Hello, my friend, and welcome to Orbital Dreams. There is a mystery hiding in almost every room you've ever entered. It may be in the window beside you, in the screen you looked at today, in a mirror, a bottle, a lens, or a quiet glass of water on a table. Glass feels so ordinary that it almost disappears. But scientifically, it is one of the most unusual forms of matter we live with every day. It is solid but not crystalline, still but not completely simple, transparent but not empty, strong in some ways, fragile in others. And even now, the deepest theory of how glass becomes glass remains unfinished. Tonight we'll follow glass from sand and fire into disorder, stillness, cracks, light, and one of the quietest unsolved questions in physics. So settle in, my friend, forget your worries, breathe slowly, and let's begin. Chapter 1. The ordinary material that should not be so strange. Tonight we begin with glass, because this quiet, ordinary material hides one of the deepest mysteries in the science of matter. A mystery sitting in windows, cups, lenses, screens, and mirrors all around us. At first, glass does not seem mysterious at all. It is the kind of material we stop noticing precisely because it is everywhere. It sits between us and the weather as a window. It protects the small glowing surface of a phone. It shapes light inside a camera, a telescope, or a pair of glasses. It holds water on a table, preserves food inside a jar, and turns a dark room into a place where the outside world can enter without wind, rain, or cold. Glass is so familiar that it feels almost neutral, almost invisible, as if it were not really a material, but simply the absence of something else. And yet glass is not empty. It is not nothing. It is a real substance, with atoms, bonds, stresses, flaws, and a hidden internal structure. It can be clear enough to disappear from sight, hard enough to resist the pressure of a hand, fragile enough to break suddenly, smooth enough to reflect a face, and stable enough to survive for ages. It can feel simple in the fingers and deeply complicated under the mind. That contrast is the first reason glass is so fascinating. It is ordinary on the surface, but strange in its foundation. Most materials announce what they are. Wood feels fibrous. Metal feels dense and cold. Rubber feels flexible. Stone feels heavy and ancient. But glass seems to sit somewhere between categories. It has the stillness of a solid, the smoothness of a liquid surface, and the transparency of air. It lets light through, but it can also bend light. It seems delicate, but it can be made strong. It seems pure, but it can contain many ingredients. It seems motionless, but its history is the history of a liquid that was cooled into a state of arrested disorder. This does not mean that window glass is secretly flowing like honey at room temperature. That old idea is often repeated, but it is misleading. Old windows are sometimes thicker at the bottom because of how they were made and installed, not because the glass slowly poured downward through the centuries. At ordinary temperatures, common glass is much too rigid for such flow to matter on human historical timescales. It is better to think of it as an amorphous solid. Solid because it holds its shape, amorphous because its atoms do not line up in a neat repeating pattern like the atoms in a crystal. This one idea already makes glass unusual. A crystal is matter arranged with long-range order. In a crystal of salt, quartz, or diamond, the atoms repeat in a pattern that can extend across the material. The pattern may be complex, but it is not random. Glass is different. In common silica-based glass, atoms are bonded into a network, but that network is not arranged like a perfect tiled floor. It has local structure because atoms still follow rules of bonding, but it lacks the long repeating order of a crystal. It is not chaos in the careless sense. It is not a pile of atoms thrown together without rules. It is a kind of organized disorder. That phrase, organized disorder, is one of the keys to understanding why glass is so scientifically interesting. The atoms in glass are not free like atoms in a liquid, moving easily past one another. But they are also not arranged like a crystal, locked into a repeating architecture. They occupy a middle world. They are held in place, but not in the most orderly possible arrangement. They remember, in a sense, the disorder of the liquid from which they came, but they behave in daily life like a solid. This is why glass can feel almost like a frozen moment. When a glass-forming liquid cools, its internal motion slows. The atoms and molecules still have thermal motion, but their ability to rearrange becomes more and more limited. Instead of suddenly becoming a crystal at one sharp freezing point, the material can pass through a range where it becomes increasingly stiff. Its viscosity rises enormously. Movement that once happened easily becomes rare. The structure falls out of equilibrium. Eventually, the material can no longer explore all the arrangements available to it. It becomes trapped in one disordered arrangement, not because that arrangement is perfectly stable, but because the path out of it has become too slow. This process is called the glass transition, and it is one of the most beautiful puzzles in condensed matter physics. It is not a simple freezing process like water becoming ice. When water freezes, its molecules arrange into a crystalline structure, and the transition is sharp and familiar. Glass formation is more gradual and more subtle. The material becomes solid-like without building a crystal. It gains rigidity without gaining long-range order. It becomes something can knock on, hold, cut, polish, and break, while still carrying within itself the disordered memory of a liquid. That is why a pane of glass can look so calm and finished, while its deepest explanation remains unfinished. Scientists understand many things about glass. They know how to make it, strengthen it, color it, shape it, and measure its properties. Engineers can design glass for windows, screens, laboratories, buildings, spacecraft, and optical instruments. But the deepest theoretical question of why glass-forming materials slow down so dramatically, and how exactly a liquid becomes glass without crystallizing, remains a rich and active area of research. Glass is not mysterious because we know nothing about it. It is mysterious because we know a great deal, and still the center of the question remains strangely difficult. Even its transparency, the feature that makes glass feel almost immaterial, depends on real physical conditions. Light is not simply passing through a magical void. In common glass, visible light can travel through because the material does not strongly absorb those wavelengths, and because a well-made piece of glass does not scatter the light too much. The electrons in the material do not easily take in the energy of visible light in a way that would make the glass appear opaque. At the same time, careful manufacturing reduces bubbles, cracks, crystals, and impurities that would scatter light and make it cloudy. The result is a solid object that can stand between you and the world while still allowing the world to be seen. That single fact is quietly astonishing. A wall stops your view because light cannot pass through it in an orderly way. A metal reflects or absorbs much of the light that reaches it. A stone scatters light from its surface. But glass can let an image cross through matter. It can allow a tree, a cloud, or a night sky to appear on the other side almost undisturbed. It's not invisible because it is absent. It is invisible because its internal physics happens to cooperate with visible light. And then, with the slightest change, glass can stop being invisible. Add certain metal ions and glass becomes green, blue, amber, violet, or red. Change its surface and it becomes frosted. Fill it with tiny bubbles or crystals and it becomes milky. Shape it into a lens and it bends the paths of light. Coat it with thin layers and it can reflect some colors while transmitting others. Heat and cool it in controlled ways and it can become stronger or more resistant to sudden temperature changes. Glass is not one thing only. It is a family of materials, and its quiet appearance hides a wide range of possible behaviors. The history of glass also shows how deeply human life has been changed by this strange state of matter. Long before modern physics could describe amorphous solids or electron energy levels, people learned that sand and mineral ingredients could be transformed by fire into something hard, smooth, and luminous. Glass became beads, vessels, windows, mirrors, lenses, and eventually instruments of science. Without glass, the microscope would not have opened the living world. The telescope would not have extended human sight toward the planets and stars. The laboratory flask would not have become such a simple and powerful tool. The modern screen, the camera, the fiber that carries light through communication networks, and the precise lens that corrects vision all belong in part to the long story of glass. There is something almost poetic about that. A material whose internal structure lacks long-range order helped human beings bring order to their understanding of the world. Through glass, we saw cells, moons, distant galaxies, chemical reactions, and our own reflected faces. It gave us clearer sight while remaining scientifically unclear in its own deepest nature. It became a tool of knowledge while staying itself a puzzle. This is the quiet doorway into the mysteries of glass. We are not beginning with a distant galaxy or a rare particle hidden inside a machine. We are beginning with something close enough to touch, something that may be beside you right now, separating warmth from cold, room from sky, inside from outside. It reminds us that mystery does not always live far away. Sometimes it waits in the most ordinary materials, in the cup on the table, in the window after sunset, in the mirror that returns your face without explaining what it is made of. So as we move deeper into this story, let the simplicity of glass become a gentle anchor. There is no need to solve every mystery tonight. For now, it is enough to notice that even the quietest objects around us can carry hidden depth, and that the world remains full of wonder without asking anything urgent from us. Let the day soften a little. Let the room be still. Like light passing slowly through a clear pane, allow your thoughts to become quieter, gentler, and easier to let go. Chapter 2. From Sand to Transparency. Glass begins with a material so ordinary that it is easy to miss how strange the transformation really is. Grains of sand, touched by heat, changed by chemistry, and guided into a substance that can hold its shape while allowing light to pass through. The story usually begins with silica sand. Not every sand is equally useful for clear glass. Beach sand, desert sand, and river sand can contain minerals, crushed shells, clay, iron compounds, and organic traces. Some of these ingredients may be harmless for certain kinds of glass, but they can also cloud the final material or give it an unwanted color. For transparent glass, the starting sand must be rich in silica and relatively pure. Silica is the main framework forming ingredient in ordinary glass. It comes from quartz, a mineral made of tightly bonded silicon and oxygen atoms arranged in a crystalline pattern. A grain of quartz sand looks simple in the hand, but on the atomic scale it is already a strong and orderly structure. The bonds inside silica are difficult to break, which is one reason pure silica has a very high melting temperature. If a glassmaker tried to make common window glass from silica alone, the process would demand intense heat and a great deal of energy. Pure silica glass does exist, and it has valuable properties, especially when resistance to heat and chemical attack is important. But for everyday glass, people learned long ago that silica can be mixed with other ingredients to make the material easier to melt and shape. This is where the chemistry of glassmaking becomes quietly elegant. Soda, usually introduced through soda ash, acts as a flux. A flux is a substance that helps lower the temperature needed for melting. Instead of forcing the silica network to soften only under extreme heat, soda changes the chemistry so the mixture can become workable at lower furnace temperatures. But soda alone creates another problem. A silica soda glass can be too vulnerable to water. It may not have the durability needed for windows, bottles, or vessels. So lime, usually derived from limestone, is added to help stabilize the glass and make it more resistant to dissolving or breaking down in ordinary use. In the simplest everyday sense, common glass is the result of balance. Silica gives the material its main network and strength. Soda makes the melting process more practical. Lime improves chemical durability. Other ingredients may be added in small amounts to adjust color, heat resistance, working behavior, or mechanical strength. The recipe is not magic, but it is sensitive. A small change in composition can affect how the glass melts, how it flows, how it cools, how it resists water, and how it interacts with light. When the raw materials enter a furnace, they do not instantly become the clear glass we recognize. They pass through a messy and dramatic stage. The grains heat, react, release gases, soften, dissolve into one another, and slowly form a molten liquid. At first, the mixture can be full of bubbles, unmelted particles, and chemical unevenness. The furnace must provide enough heat and time for the ingredients to become a more uniform melt. A bubble trapped in the melt can become a visible flaw. A bit of unmelted material can scatter light or weaken the glass. A streak of different composition can distort the way light passes through. This is one reason glass seems simpler than it is. A clear pane looks calm because many invisible problems have been reduced. The raw mixture must become homogeneous, meaning the ingredients are distributed evenly enough that the material behaves consistently. The melt must be refined, so bubbles can rise and escape. The maker is not only melting sand. The maker is managing viscosity, temperature, gas release, chemical reactions, and the motion of a glowing liquid that will eventually become solid enough to cut, polish, and install. The transformation from sand to glass also requires the loss of crystalline order. In quartz sand, the atoms are arranged in a repeating crystal pattern. When the material melts, that long-range order is destroyed. The atoms no longer occupy the fixed positions of the quartz crystal. They become part of a liquid network, still bonded and still influenced by chemical rules, but no longer arranged as a repeating crystal. The important part comes during cooling. If the liquid were allowed to arrange itself into crystals, the result would not be ordinary transparent glass. It might become a crystalline ceramic or a partly crystallized material, often less transparent because crystal boundaries and tiny structures can scatter light. To become glass, the melt must cool in such a way that widespread crystallization does not take over. The atoms slow down before they can organize into a fully repeating structure. The liquid becomes increasingly stiff. Its internal rearrangements become difficult. Eventually, it becomes a rigid, amorphous solid. The word amorphous means without a definite long-range crystalline form. The atoms still have local bonding arrangements, but they do not repeat neatly across large distances. In this sense, glass is not simply sand that has hardened. It is sand whose internal order has been erased by melting and then prevented from returning as the material cools. Now comes the part that feels almost magical. Why does it become transparent? Transparency is not caused by the material being empty. Glass is full of atoms. Light passes through it because, for visible wavelengths, common glass does not absorb strongly and does not scatter the light too much. When visible light reaches a clear piece of glass, much of it can travel through because the electrons in the glass do not easily take up that light energy in a way that removes it from the beam. The light is slowed and bent compared with its path through air, but it is not mostly swallowed. In metals, electrons can respond to visible light in ways that make the surface shiny and reflective, rather than transparent. In materials with many defects, crystals, pores, or uneven internal structures, light may be scattered in many directions, making the object look cloudy or opaque. In glass, transparency depends on both chemistry and structure. The chemistry must avoid strong absorption in the visible range. The structure must avoid features that scatter visible light. Clear glass is therefore not just melted material. It is material in which absorption and scattering have been kept low enough for images to pass through. This is also why impurities matter so much. Iron compounds, even in small amounts, can give glass a greenish or brownish tint. Other elements can create blue, amber, violet, or red colors. Sometimes this is unwanted, as in a window meant to look colorless. Sometimes it is the entire purpose, as in stained glass, decorative glass, protective bottles, or optical filters. Color is not separate from physics. It is a sign that certain wavelengths of light are being absorbed more than others. What we see as a colored glass is the light that remains after the material has selectively interacted with the incoming light. Even perfectly transparent glass still changes light. It bends light because light travels at a different effective speed inside glass than it does in air. This bending is called refraction, and it is why lenses can focus images. A flat window is designed to let light pass through with little distortion, while a curved lens is designed to redirect light in a useful way. The same basic material can therefore disappear as a window, magnify as a lens, concentrate sunlight, correct human vision, or open distant worlds through a telescope. After the molten glass has reached the right condition, it must be shaped. Depending on the purpose, glass may be floated into flat sheets, blown into vessels, pressed into forms, drawn into fibers, or molded into precise parts. In each case, temperature is everything. When glass is too hot, it flows too easily. When it is too cool, it becomes too stiff to shape. Between those extremes is a working range where it behaves like a slow, glowing, highly viscous liquid. This is the state that glass artists and industrial machines both rely on. Cooling is just as important as melting. If glass cools unevenly, different parts contract by different amounts. This can create internal stress. A piece may look finished, but hidden tension inside it can make it fragile or prone to sudden cracking. To avoid this, glass is often annealed. Annealing means holding the glass at a controlled temperature and then cooling it gradually so internal stresses can relax. This step reminds us that glass is not only a chemical substance, it is also a material with memory. How it was heated, shaped, and cooled remains written into its internal stress pattern. From the outside, the final object may look effortless. A clear jar on a shelf, a window in morning light, a drinking glass beside a bed. But inside that calm object is a whole sequence of transformations. Quartz crystals lost their order. Ingredients reacted and melted together. Bubbles escaped. Impurities were managed. The molten material avoided crystallization. Light found a path through. Stress was reduced by careful cooling. The ordinary surface hides a disciplined history of heat and timing. So when we say glass comes from sand, we are telling the truth, but only the beginning of the truth. Sand is not simply turned clear. It is purified, blended, melted, reorganized, clarified, shaped, and cooled into a state that is neither a crystal nor a liquid in the everyday sense. It becomes transparent not because it has no substance, but because its substance interacts gently with the part of light our eyes can see. And perhaps that is why glass feels so quiet. It is matter that has learned to stand aside and let the world appear through it. As this chapter closes, imagine that stillness, the warmth of a room, the darkness beyond the window, and a clear pane holding its place without demanding attention. Let the thoughts soften there, with light passing through and the day slowly becoming lighter in your mind. Chapter 3. Why glass is not really a crystal. Glass looks like a solid, feels like a solid, and behaves like a solid in ordinary life. But when we look inside it carefully, we find that it is not built like the crystals that give much of solid matter its most familiar hidden order. To understand why this matters, it helps to begin with a simple idea. A crystal is not just something shiny or decorative. In science, a crystal is a material whose atoms, ions, or molecules are arranged in a repeating pattern. That pattern can continue across enormous distances, compared with the size of the atoms themselves. It may be microscopic, and we may not be able to see it with our eyes, but it is real. If you could shrink down and travel through a perfect crystal, you would find the same arrangement returning again and again, like a quiet architectural rhythm inside matter. This is true for many substances that do not look glamorous at all. Table salt is crystalline. Ice is crystalline. Many metals are crystalline. Quartz is crystalline. Diamond is crystalline. Their outward appearances can be very different, but their inner structures share a central feature: repetition. The atoms are not placed randomly. They occupy positions related to one another by symmetry and pattern. The material has an internal map. Glass breaks that expectation. A piece of ordinary glass may be hard, rigid, and smooth, but its atomic structure does not repeat in the long-range way a crystal does. Its atoms are bonded to one another, and those bonds follow chemical rules. But the pattern does not extend regularly through the whole material. It is more like a city that has neighborhoods, streets, and connections, but no single repeating grid that continues forever. Locally, there is order. Across longer distances, there is disorder. This is why glass is called amorphous. The word means that it lacks a definite crystalline form. It does not mean that the material has no structure. That would be a mistake. Glass is not a random dust cloud frozen in place. It has a network of bonds, and nearby atoms often sit at characteristic distances from one another. In silica glass, silicon atoms are typically linked to oxygen atoms in a network, and that local bonding gives the material its strength and identity. But the angles and connections vary. The network twists and wanders. It does not settle into the repeated arrangement found in crystalline quartz. The difference between quartz and silica glass is especially useful because both can be built from the same chemical ingredients. Quartz is a crystalline form of silica. Silica glass is an amorphous form of silica. The atoms involved are not the main difference. The arrangement is. In quartz, the silicon and oxygen atoms form a repeating crystalline structure. In silica glass, similar local building units connect into a continuous network without long-range repetition. The same basic chemistry can therefore lead to two very different kinds of solid matter. This is one of the quiet lessons of materials science. What matter is made of is only part of the story. How its atoms are arranged can be just as important. Carbon can appear as soft graphite or hard diamond because its atoms are connected differently. Water can be liquid or crystalline ice depending on temperature and arrangement. Silica can become quartz or glass. The identity of a material is written not only in its ingredients, but also in its structure. A crystal is often easier for scientists to describe because repetition gives the structure a kind of mathematical simplicity. If a small part of the crystal is known, the rest can often be predicted by repeating the pattern. This is not true for glass. Because glass lacks long-range order, no small repeating unit can describe the entire structure. Scientists instead use statistical descriptions. They ask how far apart atoms tend to be, how often certain bonds appear, how the network is connected, and how order fades with distance. Glass must be described less like a tiled floor and more like a landscape of probabilities. This difference can even be seen in the way materials scatter X-rays. Crystals create sharp patterns because their repeating atomic planes scatter waves in highly organized directions. Those sharp patterns act like fingerprints of crystalline order. Glass produces broader, more diffuse patterns. The broadness does not mean there is no information. It tells scientists that short-range order is present, but the long-range repetition is missing. In other words, glass has enough order to be a material with definite properties, but not enough order to be a crystal. This middle character is what makes glass so strange. It is not a liquid in ordinary conditions, because its atoms cannot freely rearrange and the material holds its shape. It is not a crystal because its atoms do not occupy a repeating lattice. It belongs to a category that feels simple in daily life, but becomes subtle when studied closely, an amorphous solid. The word solid is important. Sometimes people hear that glass has a disordered structure and imagine it must secretly be liquid. But disorder alone does not make something liquid. A liquid is defined partly by its ability to flow and rearrange under ordinary conditions. Glass does not behave that way at room temperature. Its internal motion is so limited that for everyday purposes it is rigid. It can support loads, keep its shape, and resist deformation. Its disorder is structural, not a sign that it is slowly pouring down the window. The mistake comes from confusing shape with order. We often expect solids to be ordered and liquids to be disordered. But nature is more interesting than that. A crystal is ordered and solid. A liquid is disordered and flowing. Glass is disordered and solid. It shows us that solidity and crystallinity are not the same thing. A material can be firm without being internally periodic. It can be stable without being neatly arranged. This also explains why glass does not have the same kind of sharp melting point as a pure crystal. When a crystal melts, its ordered lattice breaks down at a fairly definite temperature under a given pressure. Glass behaves differently. As it is heated, it gradually softens over a range. It becomes less rigid, more able to deform, and eventually fluid enough to shape. This gradual softening reflects the fact that there is no single repeating crystal lattice that must suddenly collapse. The material already lacks that lattice. Heating gives its disordered network more freedom to move. Still, glass is not just any disordered solid. There are many amorphous materials, some plastics, certain thin films, metallic glasses, volcanic glass, and even some forms of frozen biological material. What connects them is the absence of long-range crystalline order, but their properties can be very different because their bonds, atoms, and molecular structures differ. Glass is a broad family, not a single personality. The lack of crystalline order affects more than scientific classification. It influences how glass responds to stress, heat, and light. In a crystal, the repeating structure can create directions with different properties. Some crystals split more easily along certain planes. Some crystals bend light differently depending on direction. Glass is often more uniform in all directions, at least on a large scale, because its disorder has no single preferred orientation. This can make glass useful when optical clarity and consistent behavior are needed. But disorder also has consequences. Because glass has no perfect repeating lattice, it can contain a range of tiny structural variations. Small flaws, scratches, or internal stresses can matter greatly. A crack can concentrate stress at its tip, and because ordinary glass is not very good at deforming plastically, the crack can grow suddenly. The material may seem strong until one small defect gives failure a path. This is part of why glass can feel so paradoxical: hard but fragile, stable but sensitive, smooth but vulnerable. Crystals can also have defects, of course. Real crystals are rarely perfect. They contain missing atoms, impurities, grain boundaries, and dislocations. But the idea of a perfect crystal gives scientists a clear reference point. Glass does not have that same simple ideal. Its disorder is not a defect added to an otherwise perfect pattern. Its disorder is part of what it is. That is why glass remains intellectually rich. It asks scientists to understand order without repetition, solidity without crystallinity, and stability without a perfect lattice. It forces us to think beyond the simple categories that everyday language gives us: solid, liquid, crystal, disorder, stability. These words seem clear until glass quietly sits between them. This is also why glass feels like such a fitting object for a calm scientific journey. It does not shout its mystery. It does not look exotic. It waits in ordinary light, perfectly familiar, until we ask what kind of solid it really is. Then the familiar surface opens into a deeper question. How much order does matter need in order to become stable, useful, and real to the touch? A crystal is matter repeating itself. Glass is matter holding together without repeating. And in that difference, a window becomes more than a window. It becomes a reminder that the world does not always need perfect order to become strong, clear, and lasting. So as this chapter settles, let that thought become gentle. Not everything has to arrange itself perfectly to hold together. Not everything has to follow a flawless pattern to be useful or beautiful. Even disorder can become quiet, steady, and full of light. Chapter 4: The Liquid That Forgot How to Flow. Glass becomes truly mysterious when we stop asking what it is made of and begin asking how a liquid can lose the ability to move, not by freezing into a crystal, but by slowing so deeply that motion becomes almost unreachable. Imagine a liquid while it is hot. Its atoms and molecules are not sitting still. They vibrate, rotate, slide, and rearrange. They exchange neighbors. They respond to gravity, pressure, and the shape of the container around them. If the liquid is thin, like water, these rearrangements happen easily. If the liquid is thick, like honey or cooling syrup, they happen more slowly. But in both cases, the material still flows because its internal structure can keep changing. A glass-forming liquid follows this same basic idea at first. When it is hot enough, it behaves like a liquid. It can be poured, shaped, stirred, stretched, or allowed to settle. Inside it, the atoms are constantly seeking new arrangements. They are not moving freely like particles in a gas because they are crowded together and influenced by strong chemical bonds. But they still have enough thermal energy to rearrange. The liquid can respond to force by changing shape. As the liquid cools, something remarkable begins. The atoms and molecules do not simply stop all at once. There is no sudden universal command that tells the material to become solid. Instead, internal motion becomes slower and slower. Rearrangements that once happened easily begin to require more time. The liquid thickens, its viscosity rises. Viscosity is a measure of how strongly a fluid resists flow. Water has low viscosity. Honey has higher viscosity. A glass-forming melt, as it cools toward the glassy state, can become so viscous that flow becomes almost meaningless on ordinary human timescales. This is the heart of the phrase, the liquid that forgot how to flow. The material has not become a crystal. Its atoms have not arranged themselves into a neat repeating pattern. Yet it can no longer behave like an ordinary liquid. Its inner structure becomes trapped by slowness. It holds its shape not because it found perfect order, but because its disorder can no longer rearrange fast enough. This process is called the glass transition. It is not the same as ordinary freezing. When water freezes into ice, the molecules form a crystal. The change is sharp and easy to recognize. Liquid water and solid ice can coexist at a definite freezing condition, and energy is released as the crystal forms. The glass transition is different. It is more gradual. It takes place over a range, and the exact point where we say the material has become glass depends partly on how we measure it and how quickly we cool it. Glass formation is therefore partly a story about temperature and partly a story about time. Time is essential. A glass is not just cold liquid. It is a material whose inner rearrangements have become too slow compared with the time scale of observation. If we could wait far beyond ordinary experience, some glassy systems might slowly relax toward more stable states. But for common glass at room temperature, this relaxation is so slow that the material behaves as a solid for all practical purposes. It does not pour out of the window frame. It does not sag like warm wax. It simply holds the shape that cooling and forming gave it. This is why the glass transition is subtle. It depends on motion becoming too slow to matter, not on a visible boundary suddenly appearing. A crystal can be described as a structure. A liquid can be described by its ability to flow. Glass asks us to think in both structure and time. It has a disordered arrangement like a liquid, but its rearrangements are frozen on the time scale of daily life. It is solid because motion has become trapped. The deeper mystery is why the slowing becomes so dramatic. Cooling almost any liquid makes it more viscous. but glass-forming liquids can slow down by an astonishing amount over a relatively narrow range of temperature. A small decrease in temperature can make internal movement many times slower. The atoms are still vibrating. Heat has not vanished, but the larger rearrangements needed for flow become difficult. Each particle is surrounded by neighbors. To move significantly, it may need nearby particles to move as well. Flow becomes cooperative, as if many tiny parts of the material must find a path together. This cooperative character is one reason glass is difficult to explain completely. It is not enough to follow one atom and ask where it goes. The atom is crowded by its surroundings. Its movement depends on the movement of others. The whole liquid becomes a landscape of constraints. Some regions may rearrange sooner, others later. Motion becomes uneven. Scientists sometimes describe this as dynamic heterogeneity, meaning that different parts of the material move at different rates as the glass transition is approached. From far away, the liquid may seem uniform, but inside it, relaxation can happen in patches and waves of activity. A useful image is a crowded room where everyone wants to move, but no one has enough space to step freely. If the room is loose and open, each person can walk without much coordination. If the room becomes crowded, one person's movement depends on another person's shifting, and that person depends on another. Nothing is locked by a visible wall, but movement becomes slower because every change requires many small adjustments. A cooling glass-forming liquid is not literally a room of people, but the analogy helps show why motion can slow without a crystal forming. Still, glass is not only about crowding. Chemistry matters. Molecular shape matters. Bond strength matters. Some materials crystallize easily because their atoms or molecules can find an ordered arrangement quickly. Other materials resist crystallization because their structures are awkward, varied, or easily trapped in disordered arrangements. In silica-based glass, the network of silicon and oxygen bonds creates a connected structure that can become rigid as rearrangement slows. In other glass-forming materials, such as polymers or metallic glasses, the details are different, but the broad idea remains. The system avoids ordinary crystallization and becomes trapped in a non-crystalline solid state. The temperature associated with the glass transition is not a perfectly fixed point like a simple melting temperature. It depends on the rate of cooling. If a glass-forming liquid is cooled quickly, it has less time to rearrange before motion becomes sluggish, so it can fall out of equilibrium at a higher temperature. If it is cooled slowly, it has more time to search for lower energy arrangements before becoming rigid. This is why glass carries a kind of memory of its making. Its properties can depend on the thermal path it followed, not only on its final temperature. This memory matters in practical ways. When glass is shaped, it must be cooled carefully. If the outside cools and stiffens before the inside has adjusted, internal stresses can be trapped. These stresses may remain invisible, yet they influence how the object responds to heat, pressure, or impact. Annealing allows some of these stresses to relax by holding the glass near a temperature where internal motion is possible but controlled. The glass is not fully liquid again, but it is not completely unable to adjust. It is given enough time and warmth to settle more gently. This shows that flow is not simply present or absent. In glass science, flow exists on a spectrum of timescales. Hot molten glass may flow readily. Warm glass may deform slowly. Cooler glass may be rigid for practical purposes. At room temperature, common window glass is so viscous that calling it flowing would be misleading in everyday terms. But at higher temperatures, the same material can soften, slump, stretch, and be worked into new shapes. The liquid has not forgotten forever. It remembers how to flow when heat gives its structure enough freedom again. The glass transition is also important beyond ordinary windows and bottles. Many plastics have glass transitions. Some become hard and brittle below their transition range and rubbery or flexible above it. Certain foods, coatings, medicines, and biological materials can also enter glassy states, where molecular mobility becomes strongly reduced. This means the mystery of glass is not limited to one transparent material. It is part of a broader question about how disordered matter becomes rigid. That broader question remains scientifically alive because it sits between thermodynamics, motion, structure, and time. Is the glass transition mostly a kinetic arrest, a falling out of equilibrium because motion becomes too slow? Is there a deeper hidden order developing as the liquid cools? Why do different glass-forming materials slow down in different ways? How should we describe a solid that has no repeating lattice, yet resists deformation so completely? These questions have inspired many theories, and no single simple picture explains every glass-forming system perfectly. This is what makes the glass transition one of the most quietly profound problems in physics. It does not require a telescope or a particle accelerator to feel mysterious. It is present in a cooling melt, in a shaped lens, in the surface of a bottle, in the pane of a window after sunset. Glass is familiar because it is useful, but it is mysterious because its stillness is not the stillness of perfect order. It is the stillness of motion slowed almost beyond reach. So when you look at glass, you are looking at a material caught between possibilities. It could have flowed, but it became too slow. It could have crystallized, but it did not. It could have rearranged into a lower energy structure, but time and temperature closed the path. What remains is a rigid memory of a liquid state, held in place by the quiet patience of matter. And as this chapter comes to rest, let that image become calm. There is no hurry inside the glass now. The rushing motion has softened into stillness. The day can do the same, settling gently, letting its restless movements slow until only a clear and quiet presence remains. Chapter 5. Why some materials refuse to become crystals. The mystery of glass deepens when we realize that many liquids are not simply waiting to become crystals. Because for some materials, the path toward order is blocked by timing, chemistry, shape, and the quiet difficulty of arranging matter perfectly. Crystals may look like the natural destination of cooling. When a liquid loses heat, its atoms or molecules have less freedom to move, and it can seem obvious that they should settle into an orderly pattern. In many cases, that is exactly what happens. Water forms ice. Molten metals often solidify into crystalline grains. Minerals grow into structured forms when conditions allow. The crystal is often the lower energy arrangement, the state matter would choose if it had enough time and a clear path to get there. But nature does not always reach the arrangement that seems most orderly. A material can be pulled toward crystallization and still fail to crystallize. It can cool below the temperature where a crystal would normally be stable, yet remain liquid for a while. It can then become so sluggish that crystallization becomes unlikely before the structure is trapped. In that moment, the material does not become a crystal, it becomes glass. To crystallize, a liquid must do more than cool. It must begin order somewhere. A tiny region has to form in which atoms or molecules line up in the pattern of the future crystal. This first organized seed is called a nucleus. If the seed is too small or too unstable, it may dissolve back into the surrounding liquid. If it reaches a stable enough size, it can begin to grow. More particles join the pattern. The crystal expands. What began as a small island of order can spread through the material. This sounds simple, but it is not easy. Forming a crystal nucleus costs energy at the boundary between the ordered region and the disordered liquid around it. The new crystal may be more stable inside, but its surface creates a kind of penalty. The material must overcome this barrier before crystallization can truly begin. If the barrier is high, nuclei form rarely. If nuclei form rarely, the liquid may remain disordered long enough to become glass. Even after a nucleus appears, growth is not guaranteed. Atoms or molecules must move to the crystal surface, bind the right positions, and attach in the proper orientation. That requires mobility. If the liquid is already becoming very viscous, motion becomes slow. The particles may want, in an energetic sense, to join a crystal, but they cannot easily reach the places where they need to be. Crystallization needs both an invitation toward order and enough movement to follow that invitation. This is one of the central reasons glass can form. The cooling liquid may pass through a region where crystals are possible, but before nucleation and growth can complete the job, molecular motion becomes too limited. The material misses the crystalline exit. It does not choose disorder in any conscious sense. It simply runs out of practical rearrangement time. Some materials avoid crystallization more easily than others. A simple material made of particles that all fit neatly into one repeating pattern may crystallize readily. A material made of particles with awkward shapes, mixed sizes, strong directional bonds, or complicated chemical arrangements may struggle. Its atoms or molecules may have many nearly possible ways to connect, but no easy path into one perfect repeating structure. The liquid becomes like a group trying to arrange itself into a precise formation, while the floor is slowly becoming sticky. At first, movement is possible. Later, the formation can no longer be completed. This kind of difficulty is often described as frustration. In everyday language, frustration means annoyance. But in physics, it can mean that a system cannot satisfy all of its preferred arrangements at once. Particles may have local ways they like to sit near each other, but those local arrangements may not fit neatly into a repeating crystal across long distances. What works in a small neighborhood may not tile the whole material. The result is not complete randomness, but a blocked path toward global order. Glass-forming liquids often live in that blocked space. They may build small hints of local structure as they cool. Nearby atoms may arrange in ways that are energetically favorable. But those local structures do not necessarily join into a single repeating crystal. Instead, the material accumulates partial order, imperfect neighborhoods, and competing arrangements. Before one pattern can dominate, the whole system becomes too slow to reorganize. Impurities and mixtures can also interfere with crystallization. A pure substance sometimes has a clearer route to one crystalline structure. A mixture may have different atoms or molecules that do not all fit into the same pattern. Some may be larger, smaller, more charged, or differently bonded. This variety can disturb the growth of a crystal. It can make the liquid harder to organize. That is one reason many glasses are mixtures rather than pure substances. Their ingredients help prevent the material from settling too easily into a crystalline form. This does not mean impurity is always helpful or always desirable. In glassmaking, some impurities cause color, bubbles, weakness, or unwanted cloudiness. But controlled composition is powerful. By choosing ingredients carefully, glassmakers can influence how easily a melt crystallizes, how it flows, how it cools, how durable it becomes, and how clear it remains. The refusal to crystallize is not merely an accident. It can be encouraged by chemistry. Cooling rate matters as well. If a liquid is cooled slowly, it has more time to explore possible arrangements. If crystallization is easy, slow cooling gives crystals time to appear and grow. If a liquid is cooled quickly, it may pass through the dangerous crystallization region before crystals can take over. This is why rapid cooling can produce amorphous solids in many materials. But the required speed differs enormously. Some substances must be cooled extremely fast to avoid crystallization. Others are naturally good glass formers and can become glass under much gentler conditions. Ordinary window glass is a good glass former compared with materials that crystallize eagerly. Its chemistry allows the melt to be shaped and cooled without instantly turning into a mass of crystals. But crystallization is not impossible. If glass is held at certain high temperatures for long enough, crystals may begin to form within it or on its surface. This process is called devitrification, meaning the glass loses some of its glassy character as crystalline regions appear. In ordinary transparent glass, devitrification is often unwanted because crystals can scatter light and create a cloudy or rough appearance. In other cases, controlled crystallization can be useful, producing glass ceramic materials with special properties. This shows an important point. Glass is not the opposite of crystal in the sense of being unrelated to it. Glass and crystal can be possible outcomes from similar ingredients. The difference lies in the path. One path gives particles enough time and mobility to form a repeating structure. The other path bypasses that structure and traps the material in a disordered solid state. A glass is sometimes a mist crystal, but not in a defective sense. It is a different solution to the problem of cooling matter. The word refuse in the chapter title is poetic, of course. Materials do not decide. They obey thermodynamics and kinetics. Thermodynamics asks which state is more stable. Kinetics asks how fast a material can get there. A crystal may be favored by thermodynamics, but if the kinetic path is too slow, the material may never reach it during cooling. Glass forms in the space between what is possible in principle and what can happen in time. This distinction is useful far beyond glass. Many natural and technological processes depend on whether a material reaches equilibrium or becomes trapped away from it. Rocks can preserve histories of cooling. Metals can be strengthened or weakened by heat treatment. Polymers can become brittle or flexible depending on their molecular motion. Even some biological and food materials can enter glassy states where motion is reduced and structure is preserved. The refusal to crystallize is part of a wider story about how matter records the path it has taken. At the deepest level, glass reminds us that order is not always the final result of cooling. Sometimes cooling creates order. Sometimes it preserves disorder. Sometimes it prevents a system from reaching the order it might otherwise prefer. The outcome depends on barriers, movement, composition, shape, and time. A material does not simply become what it wants to be in the lowest energy sense. It becomes what it can become along the available path. This is why glass feels scientifically alive. It is not merely a frozen accident. It is a record of competition between crystal growth and arrested motion. It shows that matter can be caught between the pull of order and the loss of mobility. It can carry the possibility of a crystal inside itself without ever becoming one. So when a clear piece of glass rests quietly on a table, it contains a hidden story of order that almost happened. Somewhere in its past, tiny crystals might have formed and grown. Instead, the liquid passed beyond that possibility and became still before the pattern could spread. What remains is not failure, but a different kind of stability. A calm, useful, transparent solid made from a liquid that never found its crystal. And as this thought settles, let it become gentle. Not every path has to arrive at perfect order. Some things become steady by accepting their own unfinished arrangement. In the quiet of glass, there is a soft reminder that stillness can come even when life has not lined up perfectly, and that rest can begin without everything being solved. Chapter 6: The Slowest Motion in Everyday Matter. The strange stillness of glass becomes even more fascinating when we realize that it is not a perfect absence of motion, but a world where movement has become so slow that ordinary life cannot follow it. A piece of glass on a table appears completely calm. Nothing seems to shift. Nothing seems to creep across the surface. It holds the shape it was given, reflects the room around it, and lets light pass through as if it has settled forever. Compared with steam rising from a cup or water running down a sink, glass feels like the image of stillness itself. But on the scale of atoms, stillness is never quite absolute. Even in solid matter, atoms vibrate. They are not tiny frozen statues. They tremble around their positions because temperature is connected to motion. In a crystal, this motion happens around an ordered arrangement. The atoms vibrate, but they remain tied to a repeating pattern. In glass, the motion is different in character because the structure is disordered. The atoms are held in a network or crowded arrangement, but there is no long repeating lattice guiding the whole material. They can vibrate in place, and in some conditions they can make rare small rearrangements. These rearrangements are not the flowing motion of a liquid. They are more like quiet adjustments inside a crowded structure that has very little room left to change. This is where glass becomes a material of timescales. If we watch glass for a second, it is rigid. If we watch it for a day, it is rigid. If we watch it for a human lifetime, ordinary window glass still behaves as a solid. But scientists can still speak about relaxation, aging, and extremely slow structural change. These words do not mean that glass is secretly running like syrup. They mean that the disordered structure of glass is not necessarily in its most stable possible arrangement, and over time it may very slowly adjust toward lower energy configurations. The phrase physical aging is used for this kind of slow change. It does not mean aging like a living organism. Glass does not grow old through metabolism, damage repair, or biological decay. Physical aging means that a glassy material, especially after it has been cooled from a more mobile state, can slowly change its internal arrangement. Its density, stiffness, volume, or other properties may drift slightly as the structure relaxes. The changes can be very small, and in many common objects they are not noticeable in everyday use. But they matter in science and technology because precise materials often depend on stability over long periods. A helpful way to imagine this is to think of glass as a crowd that became still before everyone found the most comfortable position. People are standing close together. No one can simply walk across the room, but a shoulder may shift, a foot may move, and tiny adjustments may happen if enough space opens nearby. In glass, atoms and molecular groups can be similarly constrained. Large motion is blocked, but very small rearrangements may remain possible, especially when temperature is high enough to give the structure a little more freedom. Temperature is the great key. At ordinary indoor temperatures, common glass is far below the range where it can easily rearrange. Its viscosity is enormous. A force that would quickly deform a liquid has almost no practical effect. But if glass is heated, its internal motion becomes more active. It may first relieve stresses, then soften, and eventually become workable. This is why a glass object can seem permanently rigid in daily life and yet become shapeable in a furnace. The difference is not contradiction. It is temperature changing the timescale of motion. This helps correct one of the most persistent myths about glass. The idea that old window panes are thicker at the bottom because glass has flowed downward over centuries. The story is memorable, but it is not the correct explanation. Historical window glass was often made by methods that produced uneven sheets. When such panes were installed, thicker edges could end up at the bottom because of craft practice, chance, or stability. The unevenness is mostly a record of manufacture, not visible flow. At room temperature, common glass would move so slowly that this kind of sagging is not a realistic explanation for old windows. Still, dismissing that myth should not make us imagine glass as perfectly motionless. The truth is subtler and more interesting. Glass does not flow like a slow household liquid in any meaningful everyday sense, but it can undergo structural relaxation over time. The movement is not a steady pouring under gravity. It is a slow search within a disordered network, shaped by temperature, composition, and history. Some glasses relax more noticeably than others. Some are designed to be exceptionally stable. Others, such as certain polymers or organic glasses, can show physical aging that affects their behavior more clearly. This is why glass is often described as being out of equilibrium. Equilibrium is the state a system would reach if it had enough time to settle fully under given conditions. A crystal can be in equilibrium state for many materials because its ordered arrangement may be the most stable form. A glass is commonly a metastable state. It can persist for a very long time because the barriers to rearrangement are high. It is not necessarily the lowest possible energy arrangement, but it is trapped so effectively that it becomes real and useful. Metastability is not weakness. It is part of why glass exists. Many things in the world persist because change is possible in principle, but blocked in practice. A mountain can be unstable in a geological sense and still stand for ages. A diamond can be less stable than graphite under ordinary conditions, yet remain diamond because the path to change is difficult. In a similar way, glass can remain glass because the rearrangements needed to become something else are far too slow at normal temperatures. The slow motion inside glass also relates to internal stress. When glass is cooled or shaped, different regions may not settle in exactly the same way. If the outside cools faster than the inside, or if the object experiences uneven temperature changes, stress can become trapped. These stresses are invisible, but they are real. They can influence how glass breaks, how it responds to heat, and how reliable it is. Heat treatment can allow some stresses to relax because the atoms gain enough mobility to adjust without fully losing the shape of the object. This ability to hold stress is part of both the danger and usefulness of glass. Poorly managed stress can make glass fragile. Carefully managed stress can make glass stronger. Tempered glass, for example, is treated so that its surfaces are placed under compression while the interior holds balancing tension. This makes cracks at the surface harder to open. The material is still glass, still brittle compared with many metals, but its internal stress pattern has been engineered to change its behavior. The slow motion of glass is therefore not merely a scientific curiosity. It is something humans learn to control. On smaller scales, scientists study glassy motion by looking at relaxation processes. Some motions are relatively local, involving small groups of atoms or molecules shifting within a confined region. Other motions are larger and more cooperative, requiring neighboring parts of the material to adjust together. These processes can occur at different rates. A glass is not a single clock ticking uniformly. It is more like a quiet room full of clocks almost stopped, each moving at its own faint pace. This idea applies beyond the clear material in windows. Many polymers, the long-chain molecules used in plastics and coatings, have glassy states. Below their glass transition range, they may become hard, brittle, or stiff because molecular motion is restricted. Over time, some can physically age, becoming denser or more brittle as their chains slowly settle. In pharmaceuticals, food science, and preservation, glassy states can be important because reduced molecular motion can slow chemical changes. The same basic principle appears again. When motion becomes extremely slow, matter can hold a structure that would otherwise change. There is a calm beauty in this. Glass is not dramatic motion, it is motion nearly silenced. It is not the rush of a river, the tumble of smoke, or the restless vibration of a flame. It is a material where the story of motion has been stretched across such long times that it becomes invisible to us. The atoms still vibrate. Rare rearrangements may occur. Stresses may relax. Properties may drift in subtle ways. But to the hand, to the eye, and to the rhythm of human days, the glass is still. That stillness is one reason glass feels so trustworthy. We build windows from it because it stays in place. We make lenses from it because it can preserve a precise shape. We store things behind it because it forms a barrier without hiding what is inside. Its usefulness comes from the fact that its motion is slow enough to become structure. It is not motion removed from matter, but motion quieted into reliability. So when you see a pane of glass reflecting the evening room, it may help to think of it not as dead matter, but as matter moving too slowly to disturb you. Its hidden adjustments are far beneath the pace of the day. Its surface waits, its shape remains. It holds light, memory, and stillness in the same clear body. And now, as this chapter comes to rest, let the idea of slow motion become gentle. Not everything needs to move quickly to be alive with meaning. Some things settle, soften, and hold. Let the last activity of the day become like glass itself, quiet, steady, and almost perfectly still. Chapter 7: The Hidden Landscape Inside Glass. One of the strangest ways to understand glass is to imagine that every silent piece of it contains not one structure, but an enormous hidden landscape of possible structures, most of which it will never reach. This landscape is not a real place inside the glass. It is not a tiny mountain range hidden between atoms. It is a scientific way of thinking about all the arrangements the atoms could have taken and how much energy each arrangement would have. If the atoms are arranged in a way that is strained, crowded, or unfavorable, the energy is higher. If they are arranged in a way that fits together more comfortably, the energy is lower. The whole collection of possible arrangements can be pictured as a vast terrain, with hills, valleys, ridges, slopes, and basins. For a simple system, this landscape might be easy to imagine. A ball rolling in a smooth bowl will move downward until it reaches the bottom. Once there, it has found a stable position. But glass is not simple. A piece of glass contains an enormous number of atoms, and each atom can be connected and positioned in many possible ways. The landscape is not one smooth bowl. It is more like a wilderness of valleys within valleys, separated by ridges of different heights. Some valleys are shallow, some are deep. Some are close together. Some are separated by barriers that are extremely hard to cross. When a glass-forming liquid is hot, its atoms have enough energy to explore more of this landscape. They can move, rearrange, and pass from one region of possible structures to another. They do not consciously search, of course. Their motion is thermal, random, and governed by physical forces. But as long as motion is easy, the material can sample many arrangements. It can fall into one valley, climb out again, enter another, and keep changing. As the material cools, this exploration becomes harder. The atoms still vibrate, but large rearrangements become less frequent. The ridges between valleys become more important. The system may find itself in one basin of the landscape and no longer have enough freedom to escape. It is not necessarily in the deepest possible valley. It is simply in a valley that has become effectively closed off. This is one of the most useful ways to understand glass. Not as matter that reached perfect rest, but as matter trapped in one region of a much larger field of possibilities. A crystal, by comparison, is like a highly organized destination. Its atoms settle into a repeating structure that can often be described by a regular pattern. In the landscape picture, crystallization is a route toward a very orderly and often lower energy arrangement. But a glass does not take that route. It becomes caught in one of many disordered arrangements that are stable enough to persist. These arrangements are not identical to one another. Two glasses with the same chemical ingredients can have slightly different internal structures if they were cooled, compressed, or treated in different ways. This is why the history of glass matters. A slowly cooled glass may settle into a lower energy arrangement than a rapidly cooled one, because it had more time to explore before becoming rigid. A glass made under pressure may preserve a different density or internal organization from one made under ordinary conditions. A glass that is reheated carefully may relax some of its internal stress and move toward a slightly more comfortable arrangement. In each case, the material is shaped not only by what it is made of, but by the path it traveled through its hidden landscape. The word landscape is helpful because it gives a visual form to something otherwise almost impossible to picture. But the real object being described is mathematical and physical. It is based on the idea that the energy of a material depends on the positions of all its atoms. Move the atoms, and the energy changes. Some movements raise the energy, some lower it. Some require passing through a temporarily unfavorable arrangement before reaching a better one. Those difficult passages are the barriers. In glass, the barriers can become so important that they define what the material can and cannot do. At room temperature, a common glass may be trapped behind barriers that are far too high for ordinary rearrangement. The atoms can vibrate within their local surroundings, but they cannot easily reorganize the whole structure. The material remains solid. If the glass is warmed, some barriers become easier to cross. Small regions may relax. Stresses may reduce. At still higher temperatures, the material softens because many more rearrangements become possible. In the landscape picture, heating gives the system enough energy to move across more of the terrain. This idea also helps explain why glass can be both stable and unfinished. It is stable because it is caught in a valley and cannot easily escape. It is unfinished because there may be deeper valleys elsewhere, representing arrangements of lower energy or greater stability. The glass does not necessarily find them, because finding them would require coordinated motion across many atoms. It would need to climb barriers, pass through difficult intermediate states, and reorganize in ways that may be practically impossible at low temperature. This is a subtle point. Lower energy does not automatically mean reachable. A valley may exist, but if the path to it crosses a high ridge, the material may remain where it is for an extremely long time. Nature is full of such trapped states. A rock may rest on a ledge even though a lower position exists below. A folded paper may hold a shape even though another shape is possible. In glass, the trap is not a visible ledge or fold, but the collective difficulty of atomic rearrangement. The landscape also helps explain why glassy motion can be uneven. In some regions, atoms may sit near a barrier that is easier to cross. In other regions, the surroundings may be more constrained. As a result, relaxation does not always happen uniformly throughout the material. Some small regions can adjust before others. The glass is not a perfectly synchronized solid. It is a material whose hidden possibilities are distributed unevenly through its structure. This unevenness becomes especially important in other glassy materials, such as polymers, metallic glasses, and dense soft materials. A polymer glass may involve long molecular chains tangled and restricted. A metallic glass may involve atoms of different sizes packed in a way that avoids a crystal. A dense suspension or foam can also show glass-like behavior, where many possible arrangements are blocked by crowding. The landscape idea is broad enough to help scientists think about all of these systems, even though their microscopic details differ. In ordinary silica-based glass, the landscape is shaped by a network of silicon and oxygen bonds. Those bonds create strong local connections, but the network can be arranged in many non-repeating ways. Some arrangements have slightly different ring sizes, angles, stresses, and densities. None of this is visible when you look through a clear pane. Yet the pane's stability, brittleness, and response to heat are connected to this unseen terrain of possible structures. The hidden landscape can also help us understand why glass sometimes changes under pressure or special treatment. If a glass is compressed strongly enough, its atoms may be forced into a denser arrangement. The material may cross from one region of the landscape into another. When pressure is removed, some of that change may remain. This does not mean the glass has become alive or magical. It means the energy landscape contains more than one possible amorphous state, and external conditions can push the material between them. Some modern methods can even produce glasses that are unusually stable, as if the material has been guided into deeper valleys than ordinary cooling would allow. These glasses may have lower energy, higher density, or greater resistance to change. They are important because they show that the landscape is not just a poetic metaphor. It can be explored through experiment, simulation, and careful control of preparation. By changing the path, scientists can sometimes guide matter into states it would not easily find on its own. Still, the landscape does not solve every mystery. It gives a powerful language, but glass remains difficult because the landscape is unimaginably complex. We cannot draw it completely. We cannot list every valley. We cannot easily follow every path through it. For a real material containing countless atoms, scientists use models, measurements, and computer simulations to understand pieces of the picture, but the full landscape remains far beyond simple visualization. That is part of the wonder. A drinking glass may look like one object, but scientifically it represents a frozen choice among an almost endless set of possible atomic arrangements. It is not only a substance, it is a history. It is the record of a path through a hidden terrain, a path chosen by heat, cooling, pressure, chemistry, and time. The surface may be smooth, but the inner story is rugged. So when you look at glass, you can imagine its atoms resting in one quiet valley among countless others. They are not searching now. They are not rushing from place to place. They have settled into the shape the past gave them. Somewhere beyond their present arrangement, other possibilities remain. But the glass does not need to reach them to be real, useful, or beautiful. And as this chapter ends, let that image become peaceful. You do not have to explore every path tonight. You do not have to cross every ridge or find every answer. For now, it is enough to rest in one quiet valley held gently by stillness, while the larger landscape waits in silence. Chapter 8. Glass Beyond Windows. When glass leaves the window frame, it becomes clear that we are not dealing with a single familiar substance, but with a whole family of materials and glass-like states that quietly support medicine, communication, electronics, geology, and even life itself. The most familiar glass is the one we see through. It sits in buildings, doors, bottles, jars, screens, and lenses. Because it is so common, it can seem as though the word glass belongs mostly to flat panes and transparent containers. But scientifically, glass is much broader. It is a way matter can exist when it becomes solid without arranging itself into a repeating crystal. That idea can appear in many chemical families, not only in the silica-based material of windows. Once we understand this, glass stops being only an object in a room and becomes a principle that appears across nature and technology. One of the most important examples is optical fiber. These thin strands, often made from extremely pure silica glass, can guide light over long distances. The glass must be made with extraordinary care, because even tiny impurities or imperfections can weaken the signal. Inside a fiber, light is guided along the strand because of the way it reflects within the glass structure. The result is a material that can carry information as pulses of light. Messages, images, video calls, scientific data, and much of the modern internet depend on this quiet ability of glass to hold and guide light with very little loss. This is a beautiful contrast. A window lets light pass through and then leaves it alone. An optical fiber takes light and gives it a path. The same general family of materials that allows a room to see the sky also helps cities, continents, and laboratories speak to one another. Glass becomes not just something we look through, but something that moves information. It turns light into a messenger. Glass also lives in laboratories. Beakers, flasks, test tubes, pipettes, and reaction vessels are often made from special glass compositions because glass can be transparent, chemically resistant, and able to tolerate heat. Borosilicate glass, for example, includes boron-containing ingredients that help it resist sudden temperature changes better than ordinary soda-lime glass. This does not make it unbreakable, but it makes it useful where heating, cooling, and chemical contact are part of the work. A scientist can watch a reaction take place because the container both holds the material and reveals it. That same combination of visibility and chemical resistance matters in medicine. Glass containers can store many medicines because they do not easily react with their contents. Glass syringes, vials, and ampoules can protect sensitive substances while allowing inspection. In some medical and biological uses, glass is not merely a container. Certain bioactive glasses can bond with bone or encourage biological repair in specific contexts. Their surfaces can interact with body fluids and form mineral-like layers that help connect them with living tissue. This is a very different role from a window. Here, glass is not separating us from the world. It is participating carefully in healing. Then there is the glass in our screens. A phone or tablet feels modern, but one of its most important surfaces is still glass. Screen glass must be transparent, smooth, thin, and resistant to scratches and impacts. Some strengthened glasses are made by chemical treatment, where smaller ions near the surface are exchanged for larger ones. This creates compression at the surface, making it harder for tiny cracks to open. The screen may still break if the force is strong enough, but the physics of surface stress can make it more durable than untreated glass of similar thickness. A fragile-looking sheet becomes stronger through hidden tension and compression. Glass also appears where heat would destroy many other materials. Glass ceramics are made by starting with a glass and then encouraging controlled crystal growth inside it. This might sound like the opposite of what glass is, but it is actually a clever use of both worlds. The original glass can be shaped, and then tiny crystals can be formed in a controlled way to create useful properties. Some glass ceramics resist thermal shock very well, which is why related materials can appear in cooktops, cookware, mirrors, and technical components. They are neither ordinary glass nor ordinary ceramic, but a carefully engineered mixture of amorphous and crystalline structure. Nature also makes glass. Obsidian forms when silica-rich lava cools so quickly that crystals do not have time to grow. The result is volcanic glass, often dark, glossy, and sharp when fractured. Long before modern material science, humans used obsidian for cutting tools because its broken edges can be extremely fine. The same glassy state that makes a window transparent can, in a different composition and context, produce a natural material sharp enough for ancient blades. Glass is gentle as a lens, but it can also be sharp as stone. Lightning can create glass-like structures too, when intense heat melts sand or soil and the material cools rapidly. Meteor impacts can produce natural glasses from melted rock. These examples show that glass is not only an invention of furnaces and factories. It is one of the possible outcomes when nature heats matter strongly and then removes order faster than crystals can form. A volcano, a lightning strike, or an impact can become a glassmaker for a brief and violent moment. Some of the strangest glasses are metallic glasses. Metals normally crystallize when they solidify. Their atoms often arrange into orderly grains, giving the metal its familiar solid form. But certain metal alloys can be cooled or processed so that crystallization is avoided and the atoms freeze into an amorphous arrangement. These metallic glasses can have high strength and unusual elastic behavior. They may resist corrosion well in some compositions, and their magnetic or mechanical properties can be useful. Yet they also bring challenges, because their lack of crystalline structure can make deformation and fracture behave differently from ordinary metals. Metallic glass is fascinating because it breaks an expectation. We often imagine glass as transparent and brittle, and metal as opaque and bendable. Metallic glass is opaque like metal, but structurally glass-like. It shows that glassiness is not about being clear. It is about atomic arrangement. A material can be shiny, metallic, and non-transparent, yet still be glass in the structural sense if it lacks long-range crystalline order and has entered a glassy solid state. Polymers can also become glassy. Many plastics are made from long molecular chains. When these chains have enough mobility, the material may feel rubbery or flexible. When molecular motion becomes restricted below a certain range of temperature, the material can become hard and brittle. This is why some plastics are flexible in warm conditions, but stiff or fragile in cold conditions. Their behavior is not only about what molecules they contain, but about how much those molecules can move. A polymer glass is another reminder that glassiness is a state of slowed rearrangement, not just a transparent substance. There are even glass-like states in biology. Some organisms can survive drying or freezing, partly by entering states where molecular motion becomes extremely limited. Sugars and other molecules can help form glassy matrices that protect delicate structures by reducing movement and limiting the formation of damaging ice crystals. In cryopreservation, vitrification is used to turn water-rich systems into a glass-like solid without forming large ice crystals. This is extremely delicate because living tissues are complex and vulnerable, but the principle is powerful. Sometimes preservation depends not on ordinary freezing, but on avoiding crystals altogether. Glass can also help contain danger. Certain durable glass compositions can immobilize hazardous or radioactive waste by incorporating elements into a stable glassy matrix. The goal is not transparency or beauty. The goal is containment. A disordered network can hold atoms in place and resist chemical breakdown over long periods. In this role, glass becomes a quiet guardian, designed to keep harmful materials from moving easily into the environment. Across all these examples, one theme returns again and again. Glass is useful because it can combine qualities that do not always seem to belong together. It can be transparent and solid. It can be chemically resistant and shapeable when hot. It can be smooth but strong, disordered but stable, fragile in one form and carefully toughened in another. It can carry light, store medicine, protect screens, preserve biological material, record volcanic fire, strengthen technology, and contain waste. So glass beyond windows is not a side story, it is the larger story. The pane in a house is only the simplest doorway into a much wider world of glassy matter. Some glass is clear, some is colored, some is opaque, some is natural, some is engineered with astonishing precision. Some is made from silica, some from metals, some from polymers, and some from biological mixtures that are only glass-like in their physical behavior. The word glass stretches farther than everyday language suggests, and perhaps that is the quiet wonder of it. Glass teaches us that a material can be defined not only by how it looks, but by how its inner motion was stopped, how its structure avoided order, and how its properties were shaped by that strange stillness. The same scientific idea can live in a fiber beneath the ocean. A vial in a hospital, a volcanic stone, a phone screen, or a frozen biological sample. As this chapter comes to rest, let the wider world of glass feel calm rather than complicated. Everywhere, matter finds ways to become still without becoming simple. Let that thought soften the evening. Many forms, many uses, many hidden structures, all resting quietly in their own shapes, carrying light, memory, and silence. Chapter 9. Why glass breaks the way it does. Glass seems fragile because it can fail suddenly, but the deeper mystery is that its breaking is not random. It follows the hidden physics of stress, cracks, surfaces, and the way a brittle material carries force. When you hold a glass cup or look through a window, the material may feel smooth and continuous. It seems like one uninterrupted body, but no real object is perfectly flawless. A piece of glass can contain tiny scratches, microscopic chips, small surface defects, trapped stresses, or subtle variations left behind by shaping and cooling. Most of these features are far too small to see. They do not matter while the glass is at rest under gentle conditions. But when a force is applied, they can become the places where failure begins. This is one of the most important ideas in understanding glass. Glass is not usually weak because every bond inside it is weak. The chemical bonds in many glasses are actually strong. In a perfectly flawless piece, the material could resist much higher stress than ordinary glass usually survives. The problem is that real glass is not perfect. Its strength is often controlled by its worst flaw. A tiny crack can matter more than the average strength of the whole object. A crack is dangerous because it concentrates stress. If you pull on a smooth material, the force is spread across a broad region. But near the sharp tip of a crack, the same force becomes focused into a very small area. The sharper the crack, the more intense the local stress can become. This is why a tiny surface flaw can become the starting point of a larger break. The glass around it may seem calm, but at the crack tip, the material is under much more severe conditions. In many metals, a crack can be slowed because the material can deform plastically. That means atoms can shift and rearrange in a way that blunts the crack tip and spreads the stress. The metal may bend before it breaks. Glass behaves differently. At ordinary temperatures, common glass has very little ability to deform plastically. It is elastic up to the point of failure, meaning it can stretch or compress slightly and then return to shape, but it does not easily flow or yield around a crack. Once the stress at the crack tip becomes too high, the crack can advance quickly. This is what brittleness means in a scientific sense. It does not mean that the material is always weak. Glass can be quite strong under compression, and carefully made glass can carry significant loads. Brittleness means that when failure begins, the material has little ability to absorb the energy by permanent deformation. The crack does not have to slowly tear through a soft, yielding structure. It can run through a rigid network. The direction of force matters greatly. Glass is usually much stronger in compression than in tension. Compression pushes surfaces together. It tends to close cracks rather than open them. Tension pulls surfaces apart. It tends to open cracks and make them grow. This is why bending can be dangerous for glass. When a glass sheet bends, one side is compressed, while the opposite side is stretched. The stretched side is often where cracks begin, especially if it contains a scratch or edge defect. Edges are especially important. A large flat surface may look like the vulnerable part, but the edge of a glass object often contains small flaws from cutting, grinding, handling, or impact. An edge chip can be a powerful crack starter. This is one reason glass sheets are polished, rounded, or treated at the edges when strength matters. A smoother edge gives cracks fewer places to begin. The object may look almost the same to the eye, but its resistance to breaking can be very different. Thermal stress is another way glass can fail. When part of a glass object heats or cools faster than another part, the different regions expand or contract by different amounts. If one area tries to expand while another area restrains it, stress builds inside the material. A very hot liquid in glass that is not designed for sudden temperature change, or hot glass placed against a cold surface, can create such stress. If the stress becomes high enough at a flaw, a crack can start. Glass does not break because heat itself is mysterious. It breaks because uneven temperature creates uneven strain. Some glass compositions resist thermal shock better than others. Glass containing boron-based ingredients, for example, can expand less with temperature change than ordinary soda-lime glass. If it expands less, the stress from uneven heating or cooling can be lower. This is why different glasses are chosen for different uses. A window, a laboratory vessel, a cooking dish, and a phone screen do not all need the same properties. Their compositions and treatments are selected for the stresses they are expected to face. Moisture can also influence crack growth in some glasses. This may sound surprising because glass seems chemically quiet, but at the tip of a tiny crack, chemical reactions with water from the environment can help bonds break under stress. This process can allow cracks to grow slowly before sudden failure. It is one reason the strength of glass can depend on environment, loading rate, and time. A piece that survives a brief force may behave differently under a lower force held for a long time. When glass breaks, the pattern it leaves behind can contain information. Specialists who study fracture surfaces can sometimes identify where a crack began and how it moved. The surface may show marks, curves, branches, or textures related to the direction and speed of crack growth. To an untrained eye, broken glass may look like pure disorder. To a trained observer, it can preserve a record of stress and motion. The break becomes a kind of map. The way glass fragments also depends on how the glass was made and treated. Ordinary annealed glass may break into sharper, larger pieces because the cracks can travel through the material without a built-in pattern of controlled stress. Tempered glass behaves differently. It is made so that the outer surfaces are placed under compression while the interior holds balancing tension. Because surface compression makes cracks harder to open, tempered glass can be stronger in ordinary use. But when failure finally penetrates that protected state, the stored internal stress helps the glass break into many smaller pieces rather than a few large ones. This is not magic, and it is not a change in the basic identity of glass. It is stress engineering. By arranging compression and tension inside the object, humans change how cracks start and how they spread. The same brittle material can behave very differently depending on the invisible stress pattern within it. A pane, a screen cover, a car window, and a laboratory vessel may all be glass, but their breaking behavior is shaped by composition, thickness, surface treatment, edges, cooling history, and the stress they carry before anything happens. Laminated glass uses another strategy. Instead of relying only on glass itself, it places a flexible layer between glass sheets. When cracks form, the interlayer can hold fragments together and absorb energy. The glass may break, but the whole structure can remain more intact. This shows that preventing danger from glass is not only about making glass stronger. Sometimes it is about controlling what happens after cracks appear. Good design accepts that flaws and forces exist, then tries to manage their consequences. On the smallest scale, breaking glass is a story about bonds being separated. But on the larger scale, it is a story about how stress finds the easiest path through material. A crack does not choose, but it follows physical conditions. It advances where the energy available to open new surfaces is greater than the resistance of the material. It branches when the conditions support branching. It stops when the driving force is too small, when compression closes it, or when another material blocks it. Even a sudden fracture obeys rules. This makes glass less mysterious in one way and more mysterious in another. It is less mysterious because breaking is not just bad luck. It can be studied, predicted, reduced, and sometimes controlled. It is more mysterious because something so smooth and calm can contain hidden vulnerability. A glass object can appear flawless, while one tiny defect quietly determines its strength. The fate of the whole piece may depend on something smaller than a grain of dust. And yet this fragility is part of what makes glass remarkable. If it were soft and yielding, it would not serve as a clear, rigid window. If it flowed easily, it would not hold precise optical shapes. If it absorbed every stress by bending, it might not preserve the still surfaces that make it useful. Glass gives us clarity, hardness, smoothness, and stability, but those gifts come with brittleness. Its beauty is connected to its limits. So when glass breaks the way it does, it is revealing the hidden physics that was always present. The smooth surface, the tiny flaw, the focused stress, the rigid network, the sudden crack, the stored tension, the edge, the temperature difference, and the surrounding moisture all belong to the same story. Glass is not fragile because it is simple. It is fragile because it is strong in a very particular way, and because strength without much yielding can become sudden failure. As this chapter comes to rest, let the thought become gentle rather than sharp. Even glass, with all its hidden cracks and stresses, can hold light beautifully for a long time. Let the day release its pressure now, slowly and safely, until the mind feels less like something under tension and more like a quiet surface at peace. Chapter 10: The Unfinished Theory of Glass. Glass becomes most mysterious at the point where practical knowledge and deep understanding no longer match, because human beings can make glass beautifully, shape it precisely, strengthen it carefully, and use it everywhere, while still not possessing one complete theory that explains its glassy nature from beginning to end. This is a rare kind of scientific situation. Glass is not mysterious because it is rare. It is not hidden in a distant laboratory or buried under extreme cosmic conditions. It is close, useful, manufactured, measured, improved, and trusted. People have learned how to control it with remarkable skill. A glassmaker can adjust ingredients, temperature, cooling, color, strength, transparency, and shape. Engineers can design glass for screens, fibers, laboratories, telescopes, buildings, and medical containers. Scientists can measure its density, stiffness, heat capacity, fracture behavior, optical properties, and relaxation. In that practical sense, glass is deeply understood, and yet the deepest theory remains unfinished. The unfinished part is not the simple fact that glass lacks the long repeating order of a crystal. That much is clear. It is not the basic fact that glass forms when a liquid avoids crystallization and becomes rigid as motion slows. That is also well established. The harder question is why the slowing of motion becomes so dramatic, how rigidity emerges from a disordered liquid, and whether there is a deeper organizing principle behind the glass transition that we have not fully uncovered. The difficulty begins with the strange invisibility of the change. When water becomes ice, the structure changes in an obvious way. Molecules arrange into a crystal. The difference between liquid water and crystalline ice can be described clearly. But when a glass-forming liquid becomes glass, the visible structural change is much more subtle. The atoms do not suddenly form a neat repeating pattern. They do not announce the transition by creating a crystal lattice. Instead, the liquid gradually loses the ability to rearrange. The material becomes solid-like, but its disordered structure may look, in many ways, surprisingly similar to the structure it had when it was still a supercooled liquid. This is what makes the theory difficult. In many areas of physics, a phase transition is connected to a clear change in order. A magnet, for example, can become magnetized when many tiny magnetic moments align. A liquid can become a crystal when particles arrange periodically. In these cases, scientists can often identify an order parameter, a measurable feature that tells them what has changed. For glass, the equivalent feature is not obvious. The material changes enormously in behavior, but not in a simple visible pattern. It becomes rigid without becoming crystalline. It stops flowing without revealing a single universal structural switch. This gap between behavior and structure is at the center of the problem. The behavior changes dramatically. The relaxation time grows enormously. The viscosity rises. The material falls out of equilibrium. It begins to age. It remembers how it was cooled. It can show uneven motion, with some regions rearranging sooner than others. But the atomic arrangement does not provide one simple repeating pattern that explains everything at once. Glass seems to ask for a theory of order that is not ordinary order. Different theories approach the problem from different directions. Some emphasize the way molecular motion becomes cooperative. As the liquid cools, a particle can no longer move independently because its neighbors block the way. Rearrangement requires many particles to shift together. In this view, the growing difficulty of coordinated motion is central. The liquid becomes crowded not only in space, but in possibility. Movement demands agreement from a larger and larger surrounding region. Other approaches focus on the hidden landscape of possible arrangements. The system may have countless valleys, each representing a different disordered structure. As the liquid cools, it falls into deeper or more isolated valleys and finds it harder to escape. Rigidity emerges because the pathways between possible arrangements become blocked by barriers. This picture is powerful because it explains why history matters. A glass is not only a state of matter, it is a record of the route taken through that landscape. Another family of ideas asks whether there is an underlying thermodynamic transition hidden beneath the practical glass transition. The ordinary glass transition happens when the material falls out of equilibrium because motion becomes too slow for the available time. But some theories suggest that, if one could wait long enough and avoid crystallization perfectly, there might be a deeper transition waiting at lower temperature. Whether this hidden transition exists in real materials and how it should be understood remains part of the debate. Other theories place more emphasis on mobility itself rather than hidden structure. They ask how mobile and immobile regions influence one another, how motion facilitates more motion nearby, and how a material can become dynamically constrained. In this picture, the important question is not only where the atoms are, but where motion is possible. Glassiness becomes a story about blocked pathways of activity. Each viewpoint captures something real. Glass-forming liquids do show cooperative motion. They do seem to explore complicated landscapes of possible structures. They do fall out of equilibrium. They do show aging, memory, and uneven dynamics. But no single simple explanation has become the final, complete theory for all glasses. The challenge is that glass is not one material with one easy behavior. It is a broad class of systems. Silica glass, polymer glass, metallic glass, molecular glass, and colloidal glass can share glassy features while differing greatly in chemistry, size, bonding, and microscopic motion. A successful theory must therefore do something difficult. It must explain common patterns without ignoring important differences. It must describe why many glass-forming materials slow down so sharply as they cool. It must explain why their properties depend on cooling history. It must account for aging and memory. It must handle the lack of long-range crystalline order. It must connect microscopic motion to macroscopic rigidity. It must work across materials that look nothing alike. This is why glass is sometimes described as one of the great problems of condensed matter physics. Condensed matter physics studies the behavior of matter made from many interacting parts, such as solids, liquids, magnets, superconductors, and soft materials. The glass problem belongs there because it is a many-body problem. The behavior of the whole cannot be understood by watching one atom alone. Each particle is constrained by its neighbors, and those neighbors are constrained by others. The mystery grows from interaction. Modern experiments and simulations have made the problem clearer, even if they have not closed it. Scientists can now observe and model glass-forming systems in ways that were once impossible. They can track particles in certain soft materials, simulate simplified glass formers on computers, measure relaxation over wide ranges of time, and prepare unusually stable glasses. These tools have revealed details of dynamic heterogeneity, structural relaxation, and the role of preparation history. The mystery has not disappeared. It has become sharper. That is often how science progresses. An old mystery does not always vanish when instruments improve. Sometimes it becomes more precise. Instead of asking vaguely why glass is strange, scientists can now ask more careful questions. What length scales grow as a liquid approaches the glassy state? What exactly controls the dramatic increase in relaxation time? How much of the behavior is governed by structure, and how much by dynamics? Why do some materials form glass easily while others crystallize? What makes a glass stable? Can we predict glass properties from composition and processing alone? These questions are not only philosophical, they matter for technology. Better understanding of glassy states can help design stronger materials, more stable medicines, better polymers, improved electronic materials, and more reliable optical components. It may help scientists control aging, brittleness, durability, and thermal response. The unfinished theory is not isolated from practical life. It sits beneath many materials we already depend on. But even without future applications, the glass problem is meaningful because it reveals something profound about matter. Glass shows that solidity does not require crystal order. It shows that a material can become rigid because motion becomes constrained. It shows that history can be stored in structure. It shows that disorder is not always a lack of form, but sometimes a form too complex to summarize simply. The unfinished theory of glass is therefore not a failure of science. It is one of science's invitations. It reminds us that familiar things can remain deep and that understanding can have layers. We can know how to make something, use it, improve it, and still not fully understand the principle that gives it its quiet nature. There is humility in that. There is also excitement. A window, a lens, a fiber, a screen, a vial, a volcanic shard, a polymer surface, a metallic glass, all of them point toward the same unfinished question. How does disordered matter become solid? How does motion vanish into stability? How does a liquid become a lasting object without becoming a crystal? For now, glass continues to answer in its own quiet way. It does not explain itself. It holds its shape. It lets light pass. It breaks according to hidden stresses. It remembers heat, cooling, and time. It stands between order and disorder, between liquid history and solid presence, between what science already knows and what remains beautifully unresolved. And as this final chapter settles, let that unfinishedness feel peaceful. The world does not need to be completely explained for it to be trusted, touched, or admired. Some mysteries can remain beside us without disturbing us. Like glass in a dark window, they can hold the night gently, reflect a little light, and remind us that even the ordinary world is deeper than the day has time to notice. And now, my friend, we've reached the end of our quiet journey through the mysteries of glass. We began with something ordinary, something almost invisible in daily life, and found a hidden world of sand, heat, transparency, disorder, slow motion, fragile strength, and unfinished science. Glass reminds us that mystery does not always live far away. Sometimes it waits beside us, in the window after dark, in the screen gone still, or in a simple cup catching a little light. If you're still awake and would like to keep drifting, you can choose another Orbital Dreams journey and let the night carry you a little farther. But for now, rest well, my friend. Sweet dreams among the stars.